We usually think of bugs in our tech as, well, something to be squashed, right? A problem to get rid of. But what if a well-known bug in artificial intelligence wasn't a flaw at all? What if you could actually use it to make the AI fundamentally smarter? Today, we're going to dig into some fascinating research that does just that, turning a weakness into an incredible breakthrough.
So just take a look at these two images. On the left, you've got a perfectly clear photo of a goldfinch. An AI can nail this, no problem, almost every single time. But the stylized image on the right, that's a whole different ballgame. To you and me, it's obviously a goldfinch, but an AI, it can get completely baffled. And this isn't just about pretty art. It points to a really deep vulnerability in how AI actually sees the world.
So you gotta ask, right? How does an AI really process an image to begin with? And maybe more importantly, what happens when we intentionally try to trick it? As it turns out, the answers lead to a totally new and way more powerful method for training AI.
Okay, so to really get the breakthrough here, we've got to go back to basics. Let's pull back the curtain a little and look at how a modern AI, specifically something called a convolutional neural network, even learns to recognize things in the first place. The real workhorse of modern image recognition is the convolutional neural network, or CNN for short. You can kind of think of it as a specialized brain that's just built for visual stuff. I mean, an image is just a grid of pixels, right? So CNNs are designed perfectly to scan them and find all the important patterns hiding inside. And what's so cool is that this process is a lot like how our own vision works. When you see a koala, your brain isn't sitting there analyzing every single pixel. Nope, you're spotting the key features. You see the fluffy ears, that big nose, the round eyes. A CNN learns to do the exact same thing. It just uses math to do it. So, how does it actually see that koala? Well, it happens in layers. First, it scans the image with these little filters to find basic stuff. Like the curve of an ear or the edge of a nose. Next, it has to decide which of those features are actually important. Think of it like taking a highlighter to the most koala-like parts. Then it kind of zooms out and simplifies things to get the big picture. That way it can recognize the koala whether it's up close or far away. And finally, it pulls all those features together to make its final guess. Yep, that's a koala. Now this whole feature detection system is incredibly powerful, but it has a hidden flaw. It can be fooled in ways that are completely invisible to you and me. It's something called an invisible attack. And this isn't some new discovery. Researchers have known about this for years. As the authors of the paper we're looking at put it, these adversarial examples are pretty much seen across the board as a major threat to how reliable these AI systems can be. So what exactly is an adversarial example? Well, imagine an image that's been altered ever so slightly. To our eyes, it looks exactly the same as the original. But for a CNN, tiny, carefully calculated bits of what looks like noise have been added. And that noise is designed to completely throw off its feature detectors, making it misclassify the image and be super confident about its wrong answer. Okay, here's the real reason this whole trick works. An AI learns from thousands and thousands of clean images, so it learns the rules for what a normal photo is supposed to look like. You can call this its statistical pattern, or its distribution. But these tricky adversarial images, they're specifically designed to break those rules. They have a totally different statistical fingerprint. And when the AI sees data that doesn't fit the pattern it's been trained on, it just gets confused and makes a mistake. This whole thing is called a distribution mismatch. For the longest time, the goal was just to figure out how to defend against these attacks. But then, these researchers had this brilliant, totally counterintuitive idea. They decided to treat this bug not as a problem they had to solve, but as a tool they could actually use. They basically asked a simple question that flipped the entire problem completely on its head. What if this very weakness, this predictable way the AI gets confused, was actually a strength just waiting to be discovered? Their main idea was that this distribution mismatch was the whole issue. So instead of trying to force the tricky examples to fit the model for clean images, they thought, why not build a model that can handle both types of data, the clean ones and the tricky ones, at the same time, but in their own separate ways? And this is their super elegant solution. It's called AdProp. It's actually pretty simple when you break it down. For every clean image they use for training, they also create a tricked, adversarial version of it. The normal clean image goes down one path in the network, business as usual. But the tricky image, it gets sent down a separate parallel path. This keeps the two different statistical fingerprints, the normal and the weird, from messing with each other. The AI then learns from both paths at the very same time, basically becoming an expert at recognizing not just real-world images, but also the very tricks that were designed to fool it.
Okay, so the idea sounds pretty clever, right? But the real question is, does it actually work? Well, let me tell you, the results weren't just good, they were completely record-breaking. Let's take a look at the numbers. Now, AdProp did improve accuracy on the standard clean dataset, but honestly, that's not even the most exciting part. The real magic happened when they threw the hard stuff at it. When the AI had to deal with corrupted, adversarial, or even those stylized images from the beginning, the performance gains were huge. We're talking up to a 7% improvement. This proves the new model wasn't just a tiny bit better, it was fundamentally more robust. It was tougher.
I mean, the results really do speak for themselves. You compare it to standard training, and AdProp is the clear winner. But what's even more impressive is that it beat previous attempts at what's called adversarial training. This shows that just showing the AI tricky examples wasn't enough. The key, the real missing piece of the puzzle, was teaching it how to handle them on a completely separate path.
So what did all this lead to? Well, with a slightly bigger model, this AdProp technique achieved a jaw-dropping 85.5% accuracy on the top 1 ImageNet benchmark, which is the gold standard in the field.
And to put that number in perspective for you, this was a new state-of-the-art record. It even beat a model that had been trained on 3.5 billion Instagram images. That's 3,000 times more data. And that other model had almost 10 times the parameters. AdProp got a better result by being smarter, not just by being bigger. So in the end, by embracing what everyone thought was just a flaw, these researchers unlocked a whole new level of performance and robustness in AI. It's just a powerful reminder that sometimes the biggest breakthroughs don't come from fixing a problem, but from looking at it in a completely different way. And it leaves you with one last question to chew on. What other so-called bugs are we trying to fix right now when we should be trying to understand them as features, hiding in plain sight?